It's a great pleasure to have Adam Levine here from MIT, and he's going to tell us about periodic dilaton gravity and double scale SYK. Adam, over to you.
Hi, yeah, thanks for the invitation to speak. Sorry again about the other week. Yeah, I was saying to Ankar, it's amazing how hard just simple time shift is to understand sometimes. So, okay. So, yeah, this is, I'm going to be talking about a couple of papers that came out in the last year or so that were inspired by, is there a way for me to, sorry, I guess, how do I do the pointer? Sorry, 1 second. Does anyone know how to, I haven't given a Zoom talk in a while and I forgot how to get the pointer to work. Oh. Uh-huh. Spotlight. No, that's not it. Okay, well, I can go without it for now. Anyway, sorry. So as I was saying, this is based on some work that was done with my collaborators, but it was inspired by work that was originally done by just my collaborators without myself, and I got interested in this. I had been thinking about similar things, and so okay, so what am I going to talk about today? The big question that we're after is, can we understand a two-dimensional gravity dual to a finite cut matrix integral? And by finite cut matrix integral, I mean one that's not in the double scaling limit. So I have in mind here the setup or the correspondence between JT gravity and a double scaled matrix integral, where you have a density of states which looks like it has semi-infinite support. So it has a minimum energy state, and then it goes up from there and has sort of a Cardy-like behavior at high energies. But lately, we've gotten interested in these models of double-scaled SYK, which is an example of a system that seems to have a gravity-like behavior, but also has a minimum energy and a maximum energy in its spectrum. So it has a finite number of states, and in this sense, it's really a UV finite version of holography. Now, there's a lot of people have been discussing connections between the double-scaled SYK model and possibly de Sitter space. I won't have anything to say about that, although I'll point out some similarities between the model that we're going to study and something like Schwarzschild de Sitter. But it's just suggestive at this point. It's not concrete. I should also give a warning that I've already on this slide, I've overloaded the term double scaled, and this is a common confusion. When I say double scaled in the matrix integral sense, which is the sense that I will probably say more in this talk, I mean it in where you take a matrix integral and you take n to infinity, but also dial couplings in the matrix integral so that you zoom in on the edge of the spectrum in a coordinated fashion. That's one double scaling limit. In SYK, there's a different double scaling limit which have to do with the parameters of the model. I don't even want to describe what that is because it, to be honest, won't be important for this talk. So whenever I say double scaled, I won't mean that version. Okay.
So you're outside the double scale, but you're still interested in the large n.
Large n, but double scale, but outside double scale. That's right. Mm-hmm. Yeah. I mean, large n, but so yeah, that's a good point. Usually when people discuss double scaled SYK, they have in mind taking n to infinity, and they generally don't discuss high orders in 1 over n, or let alone non-perturbative effects in 1 over n. We will be discussing some non-perturbative effects, and the goal is to actually capture a full non-perturbative sort of genus expansion of this matrix integral outside the double scaling limit in terms of some gravity theory. That's the ultimate goal, and this is an idea that goes back. Well, my understanding is that it goes back to work by Gopal Kumar, and then also there was a paper that I've gotten interested in by Razmat, and I'm sure many other people. This is my ignorance on this, but also recently there's this nice work by Gopal Kumar and Edward Mazenk where they are trying to kind of answer this exact question. Although we're going to be interested in a dilaton gravity dual, and they're it's unclear how what we're going to discuss is related to what they're talking about, although I'm sure there is a connection. Okay, so what is the type of theory that we'll be interested in? The gravitational theory that we think has some connection to a matrix integral outside the double scaling limit. Well, we think that in general it has to do with something called periodic dilaton gravity. So probably many of you are familiar with at this point the type of dilaton gravity that most of us talk about, which is this Jacob-Teitelbaum gravity. So dilaton gravity is a theory of the metric and the dilaton field. It comes often from dimensional reduction from some higher dimensional theory to 2D. In the case of JT, it comes from higher dimensional from reduction from some higher dimensional black hole in the near extremal limit. But we won't be so interested in what higher dimensional theory actually gives a certain potential. So this V of phi in the action, this is the dilaton potential, and we'll just be interested in the space of theories with general dilaton potentials. In particular, in this talk, I'm going to talk about theories where the potential is periodic. Okay, so it has some periodicity set by some parameter h bar. Now, most of what I say we think is general for such potentials, but in particular, it's just simplest to consider a model where we take a simple sinusoidal function for the potential. And I'll pick this normalization h bar such that h bar becomes my classical parameter. So if I rescale my dilaton, you see I can pull the h bar out front of the action, and I can treat it as some small parameter that takes me to the classical limit, and h bar goes to zero limit. Note that I could also have taken h bar to zero here. And if I kept phi fixed, then I would have gotten back to my JT potential. Okay. So there's a limit of this theory, a classical limit of this theory where you can get back to JT. In the context of the SYK model, this happens when you zoom in on the edge of the spectrum, and you get back to this so-called cinch density of states. That's a hallmark of JT gravity. Okay, but so
Adam,
for now, yeah.
Just one question from the matrix model point of view. Should I think of h bar as this parameter which zooms in on the edge of the spectrum?
Yeah. So not quite. It could be related to that. So what I haven't, so it's a bit funny here. I'm integrating over phi, right? So what I call phi, whether it's phi or phi over h bar, is a bit meaningless. So in other words, the h bar to zero limit only takes life once you include some other observable. In particular, say you put in some boundary which has some, which you want to associate to some partition function, and then h bar will be meaningful as some low energy limit of that or something.
Makes sense. Got it. Thank you.
Yeah. For the double scaled SYK people, this h bar is like log of q, where q is this parameter which controls the Q in the sense of a Q deformation.
Okay, thank you.
Mm-hmm. Okay, so let's work in the h bar to 0 limit and just analyze the classical solutions just to get our minds straight. So you can look at solutions which have a U1 U1 symmetry, like black hole solutions, and the general form of the metric is this equation at the top. And the dilaton has some profile in the radial coordinate. And when you go through the steps of solving these equations, it turns out you can always pick a gauge, at least locally, where the dilaton is this radial coordinate. And then in that gauge, the solutions are very simple. You just take this potential that was in the action, and you construct the pre-potential, the thing, the integral of the potential, and that shows up directly in the metric in this form. So here I'm using the dilaton as a radial coordinate. So just to orient ourselves in JT gravity, this potential is linear, so the pre-potential W is quadratic, right? And so that gives you exactly, hopefully that's recognizable as the metric of Euclidean ADS. And this E parameter, I call it E because in the context of JT gravity, it plays the role of the ADM energy, and it's related to the dilaton value at the horizon. So the energy is the dilaton value at the horizon squared, which is true in JT. But more generally, this E is just some integration constant. Although what we'll see is that in the way we decide to quantize things today, or the types of observables we'll be interested in today, we do want to think of E as the energy still. It actually ends up still being the energy of the dual quantum system. Okay, so but what about in the case of sine-dilaton? In the case of sine-dilaton, this pre-potential is a cosine, potential is a sine. And the metric is periodic in phi. But so now let's look at this prefactor just to get a sense of what's going on in this geometry. Let's look at this prefactor of the d tau squared. For a given phi h, which controls this energy parameter, I look at the cosine curve and I cut it at some horizontal value at cosine of phi h, and it has two intersection points. Those intersection points are the two horizons. And then the size of this time circle varies as you go in dilaton space, right? It has a 0 at the horizon, it reaches a maximum, then it has another 0. Okay, so the solution looks like on the right, it's a closed universe. And it actually doesn't have conical singularities because of the periodicity because of the symmetry properties of the potential. And these solutions actually qualitatively look a bit like a Schwarzschild de Sitter. So in Schwarzschild de Sitter, you have a geometry which looks, say, in 4 dimensions, you have a geometry which looks like topologically like S2 times S2 in Euclidean. The dilaton parameterizes the size of one of the S2s, and the other S2 is the one I've pictured here. Okay, and the solutions look qualitatively like this, although they might have conical singularities at one or the other horizon. Yeah. In general.
Is this this is you've been working in Euclidean space so far?
So far, yeah, I'm working in Euclidean. That's right. And this is the Euclidean.
And this is the unique Euclidean solution of the equation. It's parametric somehow.
With the U1 symmetry, so with a time translation symmetry, like Euclidean time translation symmetry.
I see. I see.
Now, I mean, sorry, because the dilaton is periodic, there are also 2 pi shifts of these solutions. I should also say that. So there are actually an infinite number of such solutions, but they're all, the way we will treat this model, we will treat that as almost like a gauge symmetry. So we'll almost treat phi as a compact, having a compact range, but
and there's
it's a bit subtle. Yeah.
One such solution for every temperature site, temperature. Is that right?
Good. So the temperature. So by temperature, you mean this beta here, the periodicity of tau?
Yeah.
That actually, no. There's actually the betas are constrained to be. They have a minimum. So beta actually has a minimum value amongst these solutions. So it doesn't go to zero. There's no zero beta solution here, but there is a beta equals infinity solution.
Great. And these solutions have no boundary.
Yeah.
So they all have the same action, independent of beta?
No. They can still have So even though this is dilaton gravity, they could still have non-zero on-shell action.
But is the action a function of beta, or is it independent of beta?
It could depend on beta, yeah.
Sorry, very stupid question. I'm just not understanding. If there's no boundary and all of these solutions extremize the action, usually boundary terms change things, but if they all...
Good. Sorry. Oh, sorry. I think I misspoke. Yeah, no, you're right. They must all have the same, they all have the same on-shell action. That's right. Yes.
Okay, so it's like a one parameter set of sort of degenerate solutions as far as you'll have to integrate over.
Yes. You would have to integrate over all of these. Yeah, in principle. Sorry, I misspoke. Yeah, I'm introducing these just because I find them interesting, but I'm gonna drop them in a second and do something weirder. Unfortunately. Yeah, but I introduce these because I think it's interesting that this model has these solutions, and I think they're relevant for I think they're relevant for something. They just give you intuition that what's happening here is that this model doesn't have, at least in real dilaton space, it doesn't have asymptotic boundaries. So if you want to introduce a boundary, you have to go off into, you either have to introduce something like conical singularities, or as we'll see, we're going to end up putting a boundary off in complex dilaton space, which is very strange, but it seems to give you answers that make sense. So
sorry, and one more question. Is the one loop determinant around these solutions independent of beta?
I don't know. Sorry. Yeah, that's a good question.
Presumably it is, because otherwise it sounds like the answer to the Euclidean path integral would be divergent, because you would get, non-compact in direction. Presumably the one loop determinant is compact.
Right. Presumably, yeah.
Thank you.
Okay, that's an interesting question. Yeah, I'm not sure. Right. Okay. Good. So, there's another way of thinking about this theory, which actually, so I've motivated this by thinking about dilaton gravity, but there's another way of thinking about this theory, which has a connection to recent work on the complex Liouville string, and also will make what we do henceforth more natural. So there's a field redefinition you can do for this for this theory, which makes it look like two copies of Liouville. So you take the metric, the dilaton gravity metric, and you conformally transform it to some fiducial metric, let's say a flat metric. Then you can introduce some Liouville fields, chi plus and minus, which are related to this conformal factor and the dilaton in this way. B here, for those of you that are familiar with Liouville, is this Liouville parameter. And it's related to H bar but there's a funny factor of I. And this is why this is called the complex Liouville string. So our action ends up being, when you unpack this notator, rewrite the action in terms of these chi plus and minus fields, you get two copies of Liouville. And the central charges end up being such that at least to leading order, the central charge adds up to 26. So you can think of these as starting with regular space like Liouville, and analytically continuing one Liouville in the complex B plane up to B some value, well, B squared pure imaginary, and then you analytically continue the other one in the opposite direction in the complex B plane, such that the total central charge adds up to 26. So this was discussed in these Liouville papers. Now we're going to be treating this classically, so this fact that it adds up to 26 is not super important for us because we're not going to go to higher, yeah. But you can make sense of this as a well-defined string theory. That's the point. In these variables, the solutions to the theory look like solutions to two copies of solutions to Liouville. In the classical solutions of Liouville, you can think of, it's natural to think of this Liouville metric, where you take this fiducial metric and you multiply by these Liouville fields, so, or the exponential of the chi's. And you think of that as a conformal factor on your metric. And then the equations of motion of Liouville are equivalent to saying that this metric, this Liouville metric, is just the constant negative curvature metric. So it's just an ADS. But we have two Liouville fields, so we get two ADSs. Okay. So in other words, what's happening here is that we have our dilaton gravity metric, but it's conformally equivalent, at least in some, or we're mapping it to some ADS metric, right? Via the Liouville fields. So we can think of our solutions. It's equally good to think of our classical solutions as being labeled by ADS solutions. So this is a bit funny, but it's helpful for thinking about what we're doing.
And what does this parameter beta translate to in this ADS language?
I will explain that in a bit. Yeah, it's related. So beta ends up being related to. I'll explain it in a bit, but it ends up being related to the length of a boundary in the theory, in the 80. So we're going to introduce branes in a second, or boundaries in a second, but it'll be related to some length of that boundary. Okay. So this Liouville metric, you can relate it. So it's related to the dilaton gravity metric by a conformal factor. But what is that conformal factor? Well, you can unpack this definition of the Liouville fields, and you find that it's just related to the dilaton gravity metric. The ADS metric is related to the dilaton gravity metric by a factor of e to the I phi, plus or minus I phi, depending on which ADS you want to map to. So there are two ADSs, and they get mapped to the dilettante gravity metric by a factor of e to the plus or minus I phi. Okay, so so we have our two ADSs. They're related by e to the plus or minus I phi to our dilettante gravity metric. So that means, let's look at the minus I phi one. So there's some metric, which is this metric from before. And I put some e to the minus I phi in front of it. And this should be related to ADS disk somehow. Now, it's not related to an ADS disk in the real phi plane, but you can solve these equations. So these are two metrics that need to be equivalent. If I don't mess with the tau parameter, I can solve these equations. And solving this equation for phi gives me actually that this parameter. So I have this parameter. Excuse me. I have this parameter rho h here. This is like denoting the value of the radius at the horizon radius in ADS coordinates. This horizon radius ends up being related to the dilettante value at the horizon in our original solution. So it's rho h is sine of phi h. You can prove that by solving the previous equation between the two metrics. And then you also get an equation for phi, which looks like this somewhat complicated expression, pi over 2 plus I log rho ADS plus I cos phi. That's for one of the ADSs. The other ADS, it looks like this other expression, minus pi over 2. But you can see as you go to the boundary in the first ADS, you're going off into the complex dilettante plane in the original solution. So what this is saying is that in a sense, there's an ADS boundary off in the complex part of the geometry. And well, this is a natural place to put your boundary from, and as I'll explain in a second, it's a very natural place to put your boundary from the point of view of two copies of Liouville. Now, it's a completely unnatural place to put your boundary from the point of view of real dilettante space. So maybe you say, well, we probably should have just scrapped the dilettante description entirely and just work with the two Lieuvils. That's a fine comment. I think probably morally that's true, but we also get a lot of intuition about thinking about the dilettante gravity theory as well. So I'd like to keep both descriptions around if you'd let me. But you need to swallow this issue that I'm doing something quite weird. Okay, but if you let me do this weird thing, then I can proceed.
So now can you get new solutions by changing the boundary conditions that have this funny boundary?
It's a bit of a perspective whether you want to call them new solutions. They're sort of like the same solution, just analytically continued into a different region. They're like complexified versions of the original solution, in other words.
No, sorry, I was saying that now you view this solution in this way, and it now has a boundary.
Correct.
So could we physically change the boundary conditions at this boundary to generate new solutions?
Yeah, but they will all be, yes, but they will all still just be labeled by this phi h parameter. So what I'm going to end up finding is classically, it'll be a 2-parameter phase space of solutions. It needs to be even because phase space is even dimensional. So there's this phi h parameter, which I'll think of cosine of phi h as being like the energy. And then there's its conjugate, which is like the length of the boundary. I'll explain this in a second.
And this comment is in Lorentzian space.
I'm gonna take these ADS geometries and continue them to Lorentzian signature, yeah. But the comment that there's a 2-dimensional phase space of solutions is, also true about the Euclidean solutions as well.
So that 2-dimension is an enlargement. Earlier we had a 1-dimensional space of Euclidean solutions, right? Just labeled by beta. And now you've got a slightly larger set. Is that right? Or?
Good. Yeah. So you might think right. You might think that we started out with only a one-dimensional phase space, which is a problem. Actually, this is related. This is actually, you would have gotten confused about a similar thing in de Sitter-Schwarzschild. So there, again, you would have said, oh, there's just the mass parameter. I don't have any other parameters labeling my Euclidean solutions. But actually, when you think about it from the Lorentzian point of view, you get an extra parameter because there's a time shift mode that can have a non-trivial monodromy when you go around the spatial circle. So the spatial slice of de Sitter-Schwarzschild is like an S1 times an S2. That S1, as you go around, you can have non-trivial boost monodromy. So the solutions have some boost symmetry around the horizons. As you go around, you can boost a bit and then re-identify, and you get a new solution that's actually not gauge equivalent. It differs by like a large gauge transformation from the old one. So there is actually a conjugate. There is another parameter. So while, even though I didn't describe, I wasn't talking about the Lorentzian continuation of these solutions, there should also be a version of that story here. So I think even in the original solutions I was discussing, there should be a two-dimensional phase space solution, is what I'm saying.
Okay.
Even though it wasn't manifest in what I was doing earlier.
Okay, thank you.
Yeah, that what I was just saying there, that long aside was just basically repeating this recent work of Harlow, Monsalve, and Jefferson. Okay, so sorry, this is my bad drawing of the dilaton contour that we're taking, but imagine in dilaton space you have some you have the 0, you have 2 pi, you have pi in the middle, and what's happening is we're going from the horizon, which is at phi h, and we're going off into the complex plane to some pi over 2 plus I infinity. So this is some weird thing, but anyway, okay. Hopefully it's clear what I'm doing at a mathematical level. Okay, so now let me introduce boundaries, so then it'll be clear how many solutions we have here, and yeah. So in dilaton gravity, we can introduce a natural class of boundary conditions, which is just given by this Gibbons-Hawking York term phi k minus some function a of phi. Okay, those are that's the natural set of boundary conditions in dilaton gravity. In Liouville, there's a natural set which comes from these FZZT boundary conditions. And so the boundary conditions we're going to describe today, or the ones we'll be interested in, are where we take FZZT boundary conditions on both Liouville's. So an FZZT boundary condition is just, all you do is you have something like the Gibbons-Hawking York term, this chi k hat term. But then you also have terms which look like boundary cosmological constants for the Liouville metric. Remember, by the Liouville metric, I don't mean the g hat. I mean the g hat times this exponential factor, which, as I was saying, on shell, those things are just ADS solutions. So you should read this as turning on sort of it's like I'm turning on a brane, where the mass of the brane is conjugate to the length in ADS units, or the ADS length of the boundary. Okay. So here it looks like I have two parameters, mu plus and mu minus, and those are the two cosmological constants. But it looks like each of these is conjugate. Just staring at the action, it looks like mu plus and mu minus are each conjugate to the ADS lengths in the two ADS metrics. So now it seems like I have a 4-dimensional phase space of solutions, after I was just telling Shiraz that we have a 2-dimensional phase space. So what the heck is going on? I'll explain that later, but it turns out that that these branes are not all physically inequivalent, that there's some gauge redundancies amongst them, which brings you back to your 2-dimensional phase space. Okay, so varying the on-shell action, what you end up getting This is a quick homework exercise. You see that the on-shell action just looks like the variation of the on-shell action just looks like this. From this, staring at this, you can see what I just said, that these mu's are conjugate to the length or the metric in this ADS background. And fixing, you can either fix the ADS length or you can fix its conjugate, which are these mu's, which corresponds to fixing the extrinsic curvature in the ADS background. So we have that this that these branes, they're labeled by two parameters, which label the extrinsic curvature of the boundary in the ADS metrics. Okay. So naively, I have a four-dimensional phase space with some symplectic form on it, which looks like LADS, wedge DLADS, wedge DKADS, and then the corresponding thing for the other geometry. Don't worry too much about this minus sign. It just comes out of the details of the theory. But that's the general structure that we have here. Okay, so what are the branes that we'll be interested in? So which of these two parameter family of branes will we be interested in? Well, consider a brane where one of the ADS extrinsic curvatures is 1. So if you have a curve, a closed curve, let's say in ADS that has extrinsic curvature 1, when the ADS curvature is -2, the only such curve is at the ADS boundary. You can work that out. So the K equals 1 curve and ADS2 is at the ADS boundary. And then you can ask, well, if my curve on shell is at K ADS equals 1, where is it in the other ADS? Well, if it's off at the ADS boundary in the first ADS, that means rho ADS goes to infinity. That means phi of rho ADS is going to pi over 2 plus I infinity, which if you stare at this other expression for phi of rho ADS bar means that rho ADS bar is going to minus I cosine of phi h. So what does that mean? It's going to it's going to an imaginary value in the other ADS. Well, actually, an imaginary value for the Rindler coordinate just means that you're putting the boundary on the trumpet geometry. So in ADS, there are two types of, there's another type of constant negative curvature surface, which is the double trumpet geometry. And here it looks like we're putting our boundary at on that double trumpet geometry. So you can argue that that's what happens when you continue to rho complex. And what that means is that K ADS is actually just a real. It ends up being that it's a real value, and it's equal to cosine of phi h. Okay, so that means if we put one of our branes, if we put one of the FCZT parameters to 1, set it to 1. Then the other one on shell gets set to this cosine of phi h parameter. Okay, so this is why I was saying that cosine of phi h I want to think of as the energy, because remember, it's conjugate to the LADS bar length. So I want to think of LADS bar as related to the temperature and cosine of phi h as related to the energy. Okay, so the central claim of the work of what I'm going to say today is that in this Liouville squared theory, in the presence of these types of branes, these FCZT times FCZT branes, where one of them is set to 1 and one of them is cosine of phi h, that this gives the partition function or the density of states. You should think of this brane as computing like the partition function of double scaled SYK, at least to the disk level. Okay. So as I was saying earlier, this is just for these.
From the gravity point of view, the geometry, as you say, is a double trumpet with some constant extrinsic surface cutoff in the interior. Is that how I should think about it?
Yep.
Okay. Yep. And okay, and that, so the conjecture is that that's dual to double scaled SYK. It's not the standard ADS-CFT type duality, I suppose.
Well, one of these ADSs is sort of the standard ADS disk with the cutoff off at infinity. That's the first ADS, and then there's a sort of a second ADS, which is at finite finite cutoff.
I see. Okay.
Yeah, you can think of the brane as being at finite cutoff. So yeah, and in that sense, I think, yeah, in a way, we're kind of describing some kind of finite cutoff holography here. Yeah, I'm not sure what else to say about that, but.
So where should I think of the dual field theory as living?
I think on this brane, yeah, on the brane.
On the brane. So the brane. So I think I should think of the space as a product of two ADSs.
No, good. Yeah, right. So no, it's that there's one space, but there are sort of two ways of describing it in terms of an ADS metric, because there are two ways of mapping it to an ADS space. That's the conformally mapping it to an ADS space. So there was this original Dilaton gravity metric, which is that's the solution. And then we found, by thinking about it in Liouville variables, that on shell it could be mapped to ADS in two different ways.
So if I map it in the way that it makes it look sort of familiar, just the
yes.
use of real.
Yes.
Then the boundary is really just all the way at the boundary. Did you say that?
Yep.
And then the field theory lives there.
Okay. Yes, and it's just that the energy at that boundary, because of the way the boundary terms work in this theory, in these FCGT brane boundary, in the presence of these FCGT branes, the energy at that boundary is related to sort of the extrinsic curvature in this other ADS. But for all intents and purposes, if you'd like, forget about that other ADS. Okay. Right? It's yeah. Okay. So yeah, I find the least confusing or the more familiar way to think about it is there's this ADS, the boundary is off at the ADS boundary. And then there's just some funny way of figuring out what the energy, what the symplectic form is, the energy in the conjugated is. And those have to do with this other ADS.
And if I wanted to compute the partition function of the thermal partition function of the dual field theory, the quantum mechanics, and
yes,
to compute the disk partition function and maybe corrections of this ADS space. That right?
That's right. Yeah. Okay. Okay, so that's sort of the setup. So far we just said there's the sine-dilaton gravity. We can rewrite it classically as two copies of Liouville. Each copy of Liouville gives you a copy of ADS, but they're really, as I was saying, there's really just one space-time. They're just all conformally equivalent to each other. The natural set of boundary conditions are these FCZT squared boundary conditions, and their brane parameters label ADS extrinsic curvatures classically. Okay. All right, so now we're going to take a tack. We're going to use a tactic here, which is maybe not super familiar from the Liouville literature, but I actually think it's it's something you can do, and it seems to work. We're going to try and quantize this phase space of ADS solutions canonically. And the reason we're going to do that is because we learned how to quantize the phase space of ADS solutions canonically from Harlow and Jafferis. So there was this paper where they quantized JT gravity canonically. And because these solutions are just fixed ADS, it's the same sort of space of solutions, but just with a re-identification of what you call energy and what you call time. Okay, so let me just review Harlow and Jafferis. So in when you go to Lorentzian signature, so we're going to take these solutions, which I've mostly been talking about in Euclidean, and we're going to continue to Lorentzian. So Lorentzian ADS now. And when you look at the ADS2 geometries, you get this, global ADS2 looking picture. These squiggly lines are really more for JT gravity, where the dilaton goes to minus infinity there. For the purposes of this discussion, you can forget them. And the important thing is that the phase space is labeled by, in JT gravity, it's labeled by this time shift mode. So it's relative to the left boundary, how much is the right boundary time shifted? And the conjugate to that time shift mode, not surprisingly, is the ADM Hamiltonian. In JT gravity, the left and the right ADM Hamiltonians are equivalent. And they're just H. So the symplectic form takes this form. Now, to make progress, there's a different set of canonical variables that's useful in ADS. So given a time shift mode, so I can talk about the length. So given a time shift between the two left and right boundaries, there's a unique geodesic that connects the 2 points that are shifted by that amount of time. And so you can label the state at a given time by the length of that geodesic. So you can equivalently label your states by the length of that geodesic, and classically, and also you need also a momentum. So you can do a canonical transformation to these length and momentum variables. So in JT with a fixed ADS geometry, there's a unique geodesic slice connecting any two boundary points. And what Harlow and Jafferis found was that when you go through this procedure of constructing these coordinates, you find that the Hamiltonian is related to P and L in a way that makes it look like a relativistic, a non-relativistic particle and an exponential potential, like potential. So this is this Liouville quantum mechanics.
Sorry, just a couple of.
Yeah.
I should know this, but a couple of. So L is a renormalized length. It's actually infinite.
Yes, good. It's actually infinite, but you've subtracted off some infinite constant that's independent of time, so you can just get rid of it.
Okay, and P. Well, I didn't understand what P was. Please, could you say what?
P is just so given some solution, given some formula for how L depends on time and energy. You can just it's just the canonical conjugate to L. So I'm just once I have one coordinate on phase space, I can just find its canonical conjugate, right?
In the space of solutions, is it so there's a two-dimensional phase space, or there's this L and then like a black hole mass or something like that? Is that P?
Morally, yes. It controls something like you can think of it almost like the dilaton value of the horizon.
Good, right? Yeah.
Or it's just really what it is how quickly the length is changing in time, right? It's L dot. But that's related to the black hole mass. Yeah.
Okay. Thank you.
But now the point is that let's go to the ADS solutions that we get from this Liouville squared theory. And what happens, so we have our ADS metric, which takes this form. Now it's the same geometry. So the length is related to the boundary time in actually the same way, where rho h is this parameter in the metric, and delta t is sort of the boundary window time. And again, this is some renormalized geodesic length, so I've subtracted off some constant, some infinite constant here. So in particular, note that this L, the script L, lives in the range minus infinity to infinity, so it can be negative. So the solutions all take this form. They look like log of cosh. So this is probably familiar to people at large delta t. This thing grows linearly, which is just the growth of the Einstein-Rosen bridge with the black hole. So this is the same in our theory. The only thing that changes is how this parameter rho h is related to the boundary energy. So if you remember, when we mapped to ADS, we found that the dilaton was related to rho ADS in this way. And in particular, this told us that at the ADS horizon, so at the center of ADS, at rho ADS equals rho h, the dilaton takes the value sine of phi h. So that means this rho h, but I said earlier that our boundary energy was cosine of phi h, right? So that means when you plug this in, you get some more non-trivial dependence on the energy in this L of delta t. So in JT gravity, this was just a square root of h. Now it's a square root of 1 minus h squared. Okay. So this is sort of the key difference between this is where all the non-trivial stuff has happened, is this re-identification of rho h with the energy. And now, given this formula for L as a function of time and energy, you can find the conjugate variable. Now the conjugate variable has a slightly less obvious physical interpretation, but again, it still morally controls something like the energy. Actually, you can think of P as still being related to the horizon value of the dilaton. And the Hamiltonian takes this funny form, takes cosine of P. It looks like cosine of P times square root of 1 minus e to the minus L. Now, just one comment. Well, we're going to quantize this in a second. But just immediately, you can see that this Hamiltonian is shift invariant under P goes to P plus 2 pi. So if you track where this periodicity came from, it's related to the fact that our dilaton potential is periodic in the first place. Actually, you can argue that a similar construction works for any dilaton potential that's periodic, and in fact, and you'll see that there's a periodicity of the Hamiltonian in some in shifting some momentum. Okay, so to quantize this, we have to pick some operator ordering for the Hamiltonian. And the one that we'll pick is the one that gives us a connection to double-scaled SYK. I wish I had a better justification for this. I suspect that you can justify this better, this choice of operator ordering. But for now, it's just the choice we make so we get interesting answers, and it seems to lead to interesting results. So this Hamiltonian ends up being exactly the Hamiltonian, the chord Hamiltonian of double-scaled SYK. So there's a way of solving this double-scaled SYK model in terms of some auxiliary quantum mechanics, which as Henry Lin and others showed us is related to the bulk description. And as I said earlier, the periodicity of the Hamiltonian here is inherited from the potential. Now, you can see immediately that if you want the Hamiltonian to be real, that imposes that L needs to be greater than or equal to 0. So that's a bit funny, right? L started life in a range from -infinity to infinity. And now we're saying that actually, if you want the Hamiltonian to be the thing that we want it to be, it needs to be greater than or equal to 0. And furthermore, if you actually want, under the constraint that L is positive or non-negative, if you want the wave functions to be finite, you also need to sort of gauge the p shifts. So what ends up happening is that this, not surprisingly, projects you to discrete values of the length. So the length goes from being a continuous variable in -infinity to infinity to being a discrete one, a discrete non-negative variable. Okay, this is all very funny, but it seems
this seems to be, the gauging of P seems to be a key point, right? Because it's going to
key point.
So yeah. Say a little bit more about where that came from. I mean, in the UV theory, from the description. For instance, suppose I changed the potential a little bit so that it was no longer exactly periodic, then it would not be considered to gauge it.
Yeah.
But you would say that changes the physics discontinuously.
Right. I think what ends up happening there, yeah, that's an interesting question. I actually haven't thought about that. What you see happens is that these wave functions, if they have support, so you can try and solve. So this equation, let's try and solve for eigenvalues of this equation. Or sorry, eigenvectors of this Hamiltonian. If you demand that the eigenvectors only have support on lengths greater than or equal to 0, what you'll see is actually that there need to be divergences. There need to be poles at all integer lengths. So that comes from the fact that this is a recursion relation, and also the fact that it has a structure, well, a specific structure in this recursion relation, actually. So the only sensible wave functions seem to have divergences at integer lengths, unless you decide to gauge the shift symmetry. Now, if you don't have an exact shift symmetry, my guess is that those divergences, well, yeah, I'm not sure. Yeah, my guess is that those divergences will get smoothed out and be finite, and then the theory actually will make sense for continuous L, would be my guess.
Good. So could I say this as saying that you started with some potential, but it's not quite just the theory with that potential, the potential and some extra rule.
Yes.
Okay, thank you.
Yeah, I think that sounds right. To be honest, this is the stickiest part of this talk, I think, is this exact point, because we have to put it in a bit by hand. And I think a version of this story where we understand the world sheet description might actually illuminate what's going on here a bit better. Yeah, I can come back to this point at the end of the talk, but I think as you say, this is a bit of an added rule. I don't think we fully derived it, but it gives us interesting answers. So let me keep using it.
Great.
Okay, as I was saying, this length started out in this infinite range, and then we sort of truncated its support, and then also made it discrete. Now, from this resulting theory with discrete lengths and this positivity condition on the length, we can actually compute this density of states of double scaled SYK by viewing the disk as an amplitude. But it's not actually the disk. It's this fake disk, because it gets cut off sort of. You only go from the shortest available length to the shortest available length. And that's this L equals 0 state. But in the actual ADS that we started with, the L equals 0 state is some geodesic that's not off at the asymptotic boundary, right? It's not infinitely small in this conformal diagram, in other words. It's really like stuck at some value, some finite ADS boundary time difference down here. And so this is what Henry and collaborators call the fake disk. So, sorry, what I should say is the cutoff disk is the true disk, and the fake disk is the one that we called the ADS disk in the first place. So it's the thing that sort of where it's the thing where lengths sort of would be valued in this range from minus infinity to infinity, but the true disk cuts off the range. Okay, so this produces this. This was shown to produce this density of states of double scaled SYK, where you view the true disk as a transition amplitude in this quantum mechanics that we wrote down. But it's sort of related to these issues of the discreteness and the positivity of the length. Why is it that this, we had our own unique path to this Hamiltonian, and it went through this Liouville squared theory and canonical quantization. From that point of view, it's not clear why this L equals 0 state is special. Whereas in the double scaled SYK state, double scaled SYK calculation, it's obvious why the L equals 0 state is special, because it's the 0 chord state, and you can't have negative chord numbers. So in some sense, life is easier there. One comment, though, is that because we were doing canonical quantization and we were analyzing the space of solutions in Lorentzian signature, you can see that for H bounded between 1 and -1, which it is for positive lengths, then L equals 0 is actually the smallest length in this set of solutions that you can attain in Lorentzian signature. It's the smallest length over all possible Lorentzian solutions. So as a function of time, the shortest length occurs at delta t equals 0, right? Because the cosh is monotonically increasing away from delta t equals 0. And then you just have log of 1 over, so at delta t equals 0, you have log of 1 over square root of 1 minus h squared. The shortest length you can attain is at h equals 0. So in that sense, this length is sort of special. And this fact that it goes from the shortest length to the shortest length attainable in Lorentzian signature, that actually seems to be the rule that works more generally in other periodic dilaton gravity models. So in a sense, this rule is not, the only point of this slide is just that this rule is somewhat natural from the point of view of canonical quantization starting in Lorentzian signature. All right, so that's the disk story. So if you let me put in this rule that this L equals 0 state is special, then I can derive for you the disk density of states. This is not really my work. This is just basically reinterpreting this model in terms of double scaled SYK. But now we would actually like to do better. So now I'm going to start talking about non-perturbative effects in this model. In particular, if we think of this model as a finite cut, so I should say the density of states of double scaled SYK looks like this spectrum on the right. It has a minimum energy and a maximum energy. And as I was saying, you can think of it as a matrix integral outside the normal double scaling limit. And it's a fact that finite cut matrix integrals have universal spectral correlation up to some overall scale which sets E min and E max. But if you set that to 1, so if you parameterize the energy to be cos theta or minus cos theta, where theta runs from 0 to pi, then the spectral correlator, the connected part of the spectral correlator, has this form. So we know in JT gravity, this spectral correlator can be reproduced by the gravity description. So the question is, can we also reproduce this in this Liouville squared theory? I also have okay. We have 2 hours, right? Or we go till we have another like 50 minutes or something. Is that right? I think so. Okay, so to compute this, though, the spectral correlator, we need to compute the 2-point function or the amplitude in the presence of 2 of these FCZT branes. So to do this, it's useful first to understand the Hilbert space of closed universes or closed branes. So what I'm going to try to understand is this amplitude where we have on the one hand, one of these asymptotic boundaries, which I was discussing earlier, which computes the density of states, and another boundary, another closed brane, which is labeled by these mu minus and mu plus parameters. But to understand this, it's actually simpler to go back. Well, let's go back to these dilaton gravity variables briefly, because in dilaton gravity, these closed branes, in terms of these, so in terms of dilaton gravity variables, a way to label these boundaries is in terms of the length in the dilaton gravity metric and the dilaton value along the boundary. Now, it's a fact that in dilaton gravity, the mini superspace approximation is exact. This is a general thing just about dilaton gravity. And so you can just set the dilaton. You can use the spatial diffs, in other words, along the closed universe, to set the dilaton constant, basically. And the Wheeler-DeWitt Hamiltonian. So these universes, these wave functions obey some Wheeler-DeWitt constraint, and the Wheeler-DeWitt Hamiltonian, in terms of these dilaton gravity variables, has this pretty simple form in sine dilaton gravity. More generally, for periodic dilaton gravity, this sign just gets replaced with the potential in the action in the dilaton potential. And notice that this Wheeler-DeWitt equation is invariant under shifts of phi. Okay, so if you aren't careful, you'll find that your wave functions, when you go to compute them, diverge unless you sort of gauge this shift in phi. So that's what we're going to choose to do here, and if we do that, it seems to give us sensible answers. This is a bit of another sticky point, which I would like to come back to at the end, if we have time. So if we take, so this is some constraint on the space of solutions in the closed universe solutions. So and if you can take these variables and you can map them back to the Liouville variables, and you end up getting this equation that the extrinsic curvature in the ADS and the length in the of the brane in the ADS units, they're related in the two ADSs. So this is a constraint that's telling you that these brane parameters are actually not independent. Remember the KADS and KADS bar; those are the brane parameters. So I had what looked like, remember this symplectic form, which had LADS, KADS, and LADS bar and KADS bar. So it looked like a 4-dimensional phase space, but that was ignoring this Wheeler-DeWitt constraint. So there's really actually a null direction in this phase space due to the Wheeler-DeWitt constraint. And so when you mod out, you get a 2-dimensional phase space as you should. And this LADS, so the way these parameters are related is in this functional form, LADS times square root of 1 minus KADS squared needs to be equal in the two ADSs. But what is that? So it turns out that if you have the trumpet, consider the trumpet geometry in ADS, and you have a constant extrinsic curvature closed circle on that geometry, so it has some extrinsic curvature K, then the length and the extrinsic curvature are related to the length of the closed geodesic on the same geometry by this functional form. So B here is the length of the closed geodesic on the trumpet. So you can imagine sort of the picture you should have in mind is you have this B geodesic and you can slide it along the trumpet so that it's homotopic. And as you slide it to different constant extrinsic curvature curves, the length changes in a way given by this equation. Okay. So this is just repeating what I said earlier, that we had found that the symplectic form, it looked like we had a 4D phase space of branes, but actually we had a 2-dimensional phase space. And so some of these brane parameters are redundant. So it's actually better to use this variable B, which labels the length of this closed geodesic on the trumpet geometry, and you can find its conjugate in terms of the brane parameters. We'll call it P of mu minus and mu plus. Okay. Okay, so now that we understand the space of branes that we actually have, we want to compute the trumpet amplitude. So we want to look at what or the double trumpet amplitude, sorry, where we have one of our asymptotic FCZT brane boundaries on the left and one on the right. And the way we'll do this is we'll sort of cut this following the way this worked in JT gravity, we'll cut this geometry in half along the closed geodesic, and we'll sort of insert a resolution of the identity and try to compute the wave function on either side. To do this, we need two things. We need one, this overlap between the B state and the theta state, the asymptotic FCZT brane state. And we also need to know the inner product of the B states so that we can properly insert the resolution of the identity. It turns out that if you use this Wheeler-DeWitt language, you can actually compute the overlap. I can give you some more details on this, but what ends up happening is that because we're gauging this shift in phi in the Wheeler-DeWitt Hamiltonian, B actually gets discretized. So this B parameter gets discretized, and furthermore, its overlap is given by this thing here on the left. But the important point is that this discretization of B comes from the shift symmetry in phi. In a sense, phi and B are conjugate. Yeah. This factor of 1 over b here you can think of as just it's related to the fact that the proper measure in the resolution of the identity includes a factor of b because of the relative twist between the left and the right. It's the same factor b as in JT gravity. So then we want to insert the resolution of the identity, and given those overlaps, I need to include this factor of b here. So it's a sum now, not an integral, sum over b of the wave function on the left times the wave function on the right. And we want this to match with the spectral, or the conjecture is that this should match with the universal answer for the spectral correlator in a finite cut matrix integral. And you can convince yourself that the correct answer for that is just a simple cosine of b times theta. This is actually the same thing that happens in JT gravity. It's also a cosine of b times, in that case, square root of the energy. Theta here you should think of as like the dilaton. It's related to the dilaton at the horizon in the solution, right? Because the energy was cosine of phi h. And here the energy is cosine of theta. So this is actually basically the same answer in that regard as in JT. It's the only difference here is that B gets discretized instead of being continuous. Okay. So what I'm left with is I need to argue that this B theta overlap is well, we need to compute this B theta overlap and show that it's cosine of B theta. Okay, and to do that, well, let me, yeah, are there any questions about this so far? So I didn't explain exactly how this B discretization works, but I can explain more later if we have time. And but just I wanted to point out that it comes from this discreteness, this discrete shift symmetry of the Wheeler-DeWitt equation.
Sounds
good. Okay, so to compute this this overlap, we followed the work of Okiyama. So there's an interesting point here, which is that Okiyama has written several papers on double-scaled SYK, and in each paper he basically guesses the answers that we found in sine-dilaton without having access to sine-dilaton gravity. So he somehow just made some natural guesses, and they all seem to work out in this theory. So it's kind of remarkable, actually. So in a sense, all we had to do was show that sine-dilaton outputted similar things to what Okiyama has said, and then we can use his work to get us home. But the idea is we want to compute, instead of computing this amplitude where we have one asymptotic boundary at fixed energy and one boundary at fixed geodesic length b, let's instead compute something where we put in a FCZT brane of general parameter, let's say mu and mu bar. These were my mu minus and mu plus from earlier. And instead of fixing the energy on the boundary, let me fix the conjugate, the temperature. Okay. And the idea is you can think of this as a transition amplitude from one closed universe to another, or you can turn your head and work in the open string picture and think of it as a trace in this other channel. Okay. So we're going to compute this amplitude by working in this other channel, actually. And in the other channel, this FCZT, this mu and mu bar brane, just looks like some boundary condition for our universe, which Gao, Jefferson, Kolchmeyer, well, which some people call an end of the world brane in the context of JT gravity. And so what you can do now is, so now the classical solutions, you can analyze the phase space of classical solutions in the presence of these end-of-the-world branes. And again, you find their ADS solutions, but now they're cut off at some constant extrinsic curvature brane. And you can analyze the phase space of those solutions. And what you get, again, you can talk about the length of some slice that ends normally on the brane. This is following the ideas of Gao, Jefferson, Kolchmeyer. And what you end up with are Hamiltonians, which look exactly like the Gao, Jefferson, Kolchmeyer Hamiltonian. Except again, there's a redefinition of what you mean by your parameters in ADS relative to the boundary energy. So it's basically an analogous story to the disk case, but now in the presence of a brane. And the fact that the Hamiltonian you end up with is a bit more complicated. So it takes this form, this cosine of P, square root of all the stuff, whatever. It's some form, again, under a judicious choice of operator ordering. You can solve for the eigenvectors of this Hamiltonian. And with the eigenvectors of this Hamiltonian, you can resolve the identity in this trace, and you can go and compute this amplitude. Okay, so I should say this is exactly what Gao, Jefferson, Kolchmeyer did, but in the context of JT gravity. They computed this amplitude on the left in JT gravity, where there are natural branes on the left, and they computed it as a trace. And they found an answer which looks very similar to the one that we found here and the one that Okayama found, up to the fact that this B parameter, so up to the fact that it looks like you're summing over a discrete set of trumpets instead of integrating over a continuous set. And so the answer ends up looking like a Laplace transform in B of this trumpet amplitude cosine of B theta times this P of mu and mu bar. This P is the thing that earlier I said was conjugate to B. So, and it's a non-trivial thing that what comes out of this calculation when you go to compute this trace, the non-trivial part here, is that exactly that function of mu and mu bar shows up in the exponential here. Okay, so before you did the calculation, it wasn't obvious, you're doing some open string channel thing. It wasn't obvious that it was going to match with what the closed string channel calculation told you should be the conjugate to B, but it does. It gives you the right answer up to this factor of 1 minus q to the B. Now, because of the B equals 0 term here, you can see that this answer is formally divergent. This divergence was discussed by Okayama, and it's also present there in JT gravity as well. And it's just associated with a non-trivial measure that shows up when you integrate over B in the presence of one of these end-of-the-world branes. So yeah, it's not super important, but the point is you can still extract the cosine of B theta from this answer up to this measure factor. Okay, so everything seems consistent. So sorry, this equation is probably confusing people because I have an error here. In this trace of e to the minus beta h, I have fixed beta boundary conditions. On the right, I have fixed energy boundary conditions. So what I did was I had to Laplace transform in the last equation, which I dropped. So to make this equation correct, there should be an inverse Laplace transform on the temperature, inverse temperature, in trace of e to the minus beta h. But that's the basic idea. You can extract the trumpet amplitude from these brane amplitudes. So that's why I was talking about these branes, because we wanted to get to this trumpet. Okay, that was probably a lot, but hopefully the conceptual ideas here are clear. We wanted to compute these amplitudes so we can extract this trumpet amplitude, which we can then use two trumpets to get the double trumpet, and we can compose them together to get we can take two of the trumpets to compose them into a double trumpet, and from there we can check if we get the correct spectral correlations. And it seems like we do. So we can match, in a sense, the matching the density of states of double scaled SYK required some sort of rules, as Sharad said. Here we're seeing that the same set of rules also gives you the correct spectral correlation for a finite cut matrix integral. I wanted to also discuss also there's another amplitude we can compute, which is the sphere amplitude. This is often not discussed. Well, it's been discussed in JT gravity, although in JT gravity it's quite subtle because there it's an infinite answer. But part of why it's infinite there is because you're in this double scaled limit of the matrix model. Here, because you have a finite range for the energies, actually the sphere amplitude should be finite. And from the answers we have so far, we'll try to argue that it is and that it gives the correct answer. So the sphere amplitude in a matrix model should be related to sort of the on-shell action of the matrix model. So hopefully that's clear to people. So the sphere is the leading thing, right? It's the leading diagram when you don't insert anything into your matrix integral. So sort of log of the partition function of your matrix integral is the sphere. And log of the partition function at large n is just the on-shell action of the matrix integral, right? Okay. I think this is known. I just wanted to reiterate it. Now, let me start with an observation before we get to the sphere, which is that the disk, because these trumpet amplitudes are just cosines, it's natural to decompose the disk into a piece which looks like the trumpet and a piece which looks like a cap that ends on this closed geodesic. So this cap here is sort of the wave function. Yeah, it's just the wave function of the disk in this B basis. So if you write this disk density of states, if you sort of Fourier transform it into the B basis, you get some answer for psi disk. Now, working pictorially, I have a cap here, and then I have the trumpet. So morally, what I should do to get the sphere is take two caps and glue them together with the correct measure, right?
And at what value B should you do the gluing, or does that not matter? Or you sum over?
Sorry, I couldn't quite hear. B will be summed over. Is
B
that
will...
your question?
Okay. Yes.
Yeah. So I've kind of decomposed the disk by cutting along this geodesic and then inserting a complete set of states. So one way of reading this is on the left, I have the Hartle-Hawking state, and on the right, I have the theta state in the closed universe picture, and I'm kind of inserting in the middle of a set of B states. So this side B is like the overlap between the B states and the Hartle-Hawking state. So to get the sphere, I should take the square of this B wave function, and I should sum over B with the correct measure. Okay, so I should do B times psi disk squared of B. But you can write these side, so this should be the sphere, but you can write these psi disk B wave functions in terms of row disk by inverting this Fourier transform, right? So if I plug that in above for psi disk of, so if I rewrite psi disk of B in terms of an integral over the density of states, in other words, I get this formula below that the sphere partition function should be integral over two energy variables times cosine of B theta, cosine of B theta prime. Those are the two trumpets, sort of. But now the measure factor works out to be 1 over B. This just follows from the formula I've written.
Sorry, I should have asked this much earlier. This B state, it's defined with some value of the dilaton?
No, it's the length of this closed geodesic on the trumpet.
Of the closed geodesic, okay, fine.
Yeah. It's like, I think I shouldn't draw this picture horizontally. It's really a vertical picture. It's really like a de Sitter looking like thing where you have a cap which ends on some geodesic. And then the geodesic continues off to the asymptotic boundary. Or sorry, then the universe starts, the closed universe starts from this geodesic and continues off to the asymptotic boundary. And we're just computing sort of the sphere part from the cap.
And I'm trying to understand this. So B is roughly the length of this curve?
Yes. It's the length of the closed geodesic in the ADS metric, right? We're working in ADS here. And
I'm trying to understand this, intuitively understand that you have to integrate over B. So that sort of feels, if B is like, once you glue B is like the equator of the sphere?
Yeah.
And integrating over B is like you're integrating over spheres of all sizes. Is that right?
Yes.
Okay.
Exactly.
And that is a parameter because this theory, it's not a conformal theory, is it?
Yes.
Okay, thank you.
That's right.
Yeah.
Right. Good. So you want to sum over all these B's because you want to sum over all spheres. And when you do this sum down here, this expression for Z sphere gives you a log of energy 1 minus energy 2 integrated. And okay, there's minus signs and factors of 2, whatever I haven't been careful about. But you can trust me that when you're careful about all of that, you end up getting on the nose the on-shell action for the matrix integral, which involves this log. This looks like this Vandermonde determinant. You can convince yourself from the equation of motion of a matrix integral that the on-shell action, which should be like the Vandermonde together with the trace of V, where V is the potential for the matrix integral. Because the potential is related to the density of states on shell, you end up just getting that the on-shell action can be written in terms of the Vandermonde up to some free factor, and this gives you the right answer. Note, I actually haven't used anything at all about psi disk of B. So this is suggesting that every matrix integral has some interpretation in this. Every finite cut matrix integral has some interpretation in this manner, where you can rewrite the sphere partition function as two caps that have been glued and summed over. So it's a very universal result. Yeah. Okay. Okay, so what have we done so far? So in summary, we up to some, as Sharad said, some rules that we sort of need to input. We can get, but inputting a small number of rules that we still need to understand better. We can get the disk density of states of double scaled SYK, the spectral correlator, and the sphere. And all of these match what is known as the Q-deformed JT matrix integral or matrix model. This so the reason it has a different name from double scaled SYK is just because double scaled SYK, you should really think of double scaled SYK. This matrix integral, let me put it this way. This matrix integral is analogous. This matrix integral is to double scaled SYK, what JT gravity is to regular SYK. So JT gravity plus all of its higher genus corrections. So the JT matrix integral, regular SYK is not just the JT matrix integral. It has other stuff in it. So too, do we think double scaled SYK has other stuff in it? But some sort of universal or some subsector of the theory is described by this matrix integral. And in particular, this matrix integral has some non-perturbative definition, non-perturbative completion. So is this correspondence between the sine-dilaton theory and this cutiform JT matrix integral a non-perturbatively correct statement? So we think it is, although we still haven't shown it. So this is the question of higher genus corrections. This is also tied up in the fact that this sine-dilaton gravity, at least at the classical level, is equivalent to this complex Liouville string of these authors, Collier, Eberhardt, Muehlmann and Rodriguez. And there they have a non-perturbative completion of that theory treated as a world sheet theory, which is not double scaled SYK. It's a two matrix integral. Yeah, it's just not double scaled SYK.
And
they,
then they interpreted this. Was it exactly the same? How come they interpreted in terms of de Sitter, while you have? Sorry, what's the deal there? De Sitter versus ADS.
You mean because they have a discussion about de Sitter? Is that what you're referring to?
Yeah.
Their de Sitter, though, is a three-dimensional de Sitter. So I've been talking about the world sheet geometries. In other words, the geometries on the world sheet. So it's like I've been treating the world sheet theory in the small alpha prime limit, and I've been looking at the on shell world sheet geometries.
Yes, thank you.
They're when they discuss de Sitter, they're really talking about something. Well, yeah, I don't want to say it's a target. Yeah, it's more like a target space description, I guess.
Thank you.
Yeah. Okay. So what is the connection, or is there a connection between what we're doing and what they have done? Let me just comment one thing on this. So in the complex, in dilaton gravity, there's a natural set of sort of quote unquote vertex operators, which are the following integrals. So you integrate over the space-time insertions of e to the IB minus 2 pi phi. These operators have the interpretation of opening up, they open up geodesic holes in the spacetime. So they open up these closed geodesics. So in other words, in this picture here, forget about the cap. I can think of this diagram, this b theta amplitude, as computing the 1-point function of one of these vertex operators I just wrote in the presence of this FCZT brane. So I can think of this hole as really like a vertex operator insertion. I have in mind here maybe some kind of shrinking of the hole down to a point where the vertex operator sits. But what I said is that in our theory, what ends up happening is this family of vertex operators is labeled by a discrete parameter. So this B becomes discretized. Now, if you take these vertex operators for discrete B and you do this change of variables to the Liouville description, what you find is that these vertex operators actually correspond to a discrete set of vertex operators in Liouville. And there's a natural discrete set of vertex operators in these Liouville theories, which are these degenerate operators. So what we think is going on is that the operators, so in the complex Liouville string, they have a set of vertex operators which are labeled by a continuous parameter, by continuous Liouville momentum. So in the Liouville vertex operators, there's this Liouville momenta, which is morally like this B parameter. And for discrete choice of those Liouville momenta, you get these degenerate representations of Virasoro. And those degenerate representations precisely seem to correspond to the types of discrete B operators that we are considering in our theory.
So you get these degenerate representations at some particular values of momentum?
Yes.
Related to the central charges, related to the slope.
That's right. That's right.
And you get
that's right.
And your B's turn out to be exactly those values.
Yes.
Okay.
Well, they turn out to be a subset of those guys. I should say actually. So our vertex operators are like a subset of the degenerate operators.
And does degenerate mean that the OP closes among these sets? Good.
Yeah. So in general, yeah. So what we want is a theory so what we're after here, it seems, is a theory whose vertex operators are labeled by these degenerate representations in Liouville. It would be nice if they closed in the OPE. The set that closes is this 1, B set where B. So I've overloaded B here. By B here, let me call them 1, N set, where N is one of the labels in the degenerate. Is the label of the degenerate operator that we're picking. So in general, there's a two index set of degenerate operators, these M, N parameters. There's a 2 index family of degenerate operators in Liouville. And we're going to focus on the 1, N set because those operators close under the OPE. More generally, you would need to include all the degenerate operators to form a closed theory.
Okay.
So but it happens that this set, the 1, N set, is actually the ones that it's basically these operators.
The ones that your analysis would lead you to.
Yeah. Well, there's a mild thing I'm lying about here.
Sure.
The 1, N set is the ones that they're not quite these operators. They're the e to the ib without the 2 pi. Oops, sorry. They're the e to the ib without the 2 pi present. But those are the operators that are invariant under shifts of phi. So there's a subtlety here about what's going on with this 2 pi, which we're still a bit confused about. But we think the answer, well. Yeah, maybe let me not say what I think the answer is because it could be wrong. But so there is a slight subtlety about this question of the closing of the OP and exactly what operators we want. But we think the answer is that it's the 1, N set because those correspond to the ones which are invariant under discrete shifts of phi. Now, I should say there's another set. There's a set of string theories where the vertex operators are labeled by degenerate representations for minimal string theory. But there, the representation, the central charge of the theory is fixed to be, B squared to be rational so that you get a finite set of degenerate representations. Here we have an infinite set of degenerate representations, right? Because B runs over an infinite number of discrete numbers. And there is a way of getting an infinite number of degenerate representations when B, so it means like this B squared parameter in Liouville is not rational. when it's not rational, this is sometimes referred to as generalized minimal string theory. Now, generalized minimal string theory has a lot of people have discussed this in the past. It's confusing. This is just the statement is that it's morally, the thing we're after is something morally like generalized minimal string theory.
So if you did Liouville theory and you looked at just these operators and you computed the one loop partition function, would that be modular invariant?
Right. That's the question. Yeah, that's the issue. Yeah, this is something we need to check. What we think could be going on is that you can find all of these operators in the complex Liouville string. By looking at, so yeah, this is getting maybe into more detail than I wanted to go, but in the amplitudes of the complex Liouville string, you can look at the string amplitudes as a function of the external momenta, the Liouville vertex operators. And these amplitudes have poles precisely at the degenerates. And you can think of the residue of those poles as being related to the coefficients of to the amplitudes of degenerate operators. So it's a bit as if in the complex Liouville string, you haven't gauged a shift symmetry. And then when you go to these poles, the shift symmetry is becoming, because the operators become invariant under the shift symmetry, the poles are appearing because you're summing over a non-compact gauge group. So you get some factor of the volume of the gauge group. And so you want to divide out by that infinity, which is just the residue of the poles, and which gives you just the residue of the poles. And so that should be related to the amplitudes that we want. This is our conjecture, that the residue of the poles of the complex Liouville string should be related to these, to the sine-dilaton gravity model and quantized in the way that we are treating it. And what I wanted to say was that if you work in that manner, it seems more hopeful that things will be modular invariant, just because it will inherit it from the complex Liouville string.
You're saying the factor of the volume is just some overall factor. Who cares?
Right. Yeah, exactly. But this is all very much work in progress. But the question you raised, Shiraz, is a key question. Yeah, right. People have discussed this in the past, I've learned, and this is exactly the sticking point. So it's not an easy problem. Oh, okay. I'm almost out of time. Let me just end with one last comment, which is that given the data of the disk density of states and the spectral correlator, you can set up something like topological recursion, even for a finite cut matrix integral. So you still get something called something like a spectral curve, even for a finite cut matrix integral. It's just a genus zero spectral curve with a finite branch cut. And you can talk about an analog of these Weil-Petersen volumes that show up in JT gravity or their analogs in other dilaton gravity theories. And what happens, as was pointed out by Okayama, and in these papers by Norbury and Scott, is that you can define a version of these Weil-Petersen volumes where the lengths of the closed geodesics in the volumes is discrete. So we really would like to understand how sine-dilaton gravity reproduces these discrete volumes, which should be related to these amplitudes of the complex Liouville string in some way. But this is the work in progress that that needs to be done. Okay, so that's where I'll stop. We're accumulating evidence that sine-dilaton gravity is dual to a finite cut matrix integral, and if this works, then likely it works for a general periodic potential. And you can probably, yeah, well, we're not there yet, but yeah, we're working on it. So that's it. Thanks.
Question? I had two sort of very general questions, if you don't mind.
Yeah.
The first one is this. A place that in which I have previously seen something continuous becoming discrete is in Chern-Simons theory.
Mm-hmm. Mm-hmm.
You take Chern-Simons theory on, let's say, genus G times S1.
Mm-hmm.
You work out the path integral. Let's take S2 times S1 for concreteness. And
Okay.
you work out the path integral along the lines of this paper by Blau and Thompson. You have this holonomy variable on the circle direction. And then the Chern-Simons action has a K A0 F term.
Mm-hmm.
And then when you sum over all fluxes, you're summing e to the power I K A0 times n, because fluxes are integers. And you sum over n, and then use the formula that e to the power I n alpha summed over all n is the discrete delta function.
Mm-hmm. Mm-hmm.
That effectively tells you that A0 and hence the eigenvalues of the holonomy matrix become discrete.
Mm-hmm. Mm-hmm. Mm-hmm.
Note that the discretization is k times A0 is an integer, so A0 becomes discrete like integer divided by k.
Mm-hmm.
So that if the limit k goes to infinity, sort of a classical limit, there's no discretization, it's all values.
Yeah.
But quantum effects discretize this eigenvalue.
Yes. Yes.
This is a really nice mechanism. It's a sum over various saddle points, which gives a phase, and that's just the discretization comes out of the path integral in a very natural way.
Yes. Yes.
So this is like a very vague question, but I was wondering whether it might, and I don't really know what I'm asking, but I was wondering whether it might be that something like that happens in your.
Yeah, that's very possible. I think morally, that is sort of what's going on here, right? Where you sum over all the different dilaton values. So the dilaton starts life as being non-compact somehow. But when you sum over all these discrete images of the dilaton, it's making the geometry discrete somehow, because the dilaton is sort of conjugate to the geometric features. I
was wondering whether, it's just a very vague, but for instance, at some point you have this action in terms of P and L, the momentum,
yes,
the length.
Yes.
And at some point you needed to sort of assert that P's that were, that P was a periodic variable. And I was wondering whether perhaps some gravity path integral, maybe summing over some gravitational instantons, whatever, or maybe your phi's could actually show that somehow. Okay, I'll shut up. I'm just repeating this. If so, what could these? Okay, so I'll shut up.
Yeah. Right? Yeah, I feel it should. Yeah. So in one of our papers, we tried to do something like this. We tried to argue that there were gravitational saddles that were sort of the images of this discrete shift, and when you summed over all of them, you got a delta function out. That was morally what we tried to argue, but it's a bit tricky because once you pass to this canonical quantization picture, what we're missing still is sort of a more intrinsically or manifestly gravitational path integral description of what we're doing here. That would help a lot with this higher genus stuff too. Right. A lot of what we've done is very tied to this canonical quantization business. And it seems to hint at a version that should work in the gravitational path integral. Yeah. I think that's sort of the key thing that we're missing, which would probably include an effect like what you're saying.
Right. Just one quick follow-up and then I'll shut up, sorry.
Yeah.
Again, just going back to Chern-Simon's theory, there's this path integral picture that we just discussed, but there's also canonical quantization. Canonical quantization is the canonical quantization of Wheatley, right? Where he produced conformal blocks. Now, if you were naive, instead of conformal blocks, you might have thought that asserted that the answer was just all classical gauge invariants associated with your insertions. Witten, of course, was not naive, and he realized that it was sort of conformal blocks. And the difference between these two is the following: that, I mean, if you just had classical gauge invariants, then your eigenvalues in A0 would not be quantized, because you would hard measure integrals count classical signals, which would just continue. Whereas if you're doing this quantum, Westmino would kind of
right.
that quantized.
Yeah.
Now, in some way, the naive picture was wrong because you couldn't make a positive definite inner product on that Hilbert space. One pedestrian way of saying it is that if you try to enlarge your Hilbert space to include more than conformal blocks, classical invariants, I think you would have trouble with the inner product. So with this long preamble, I was wondering whether somehow the inner product will help you argue for what you want.
Yeah, it sounds very analogous to what we're trying to say here, right? Yeah, that's an interesting suggestion. Is there somewhere I can read about this problem with the inner product? That's
if I can find a reference that is clear here.
Yeah.
I will. I mean, the best place to see it is in an example. The place I've seen it is sort of in an example, which would okay, but I'll try to dig up a reference.
Okay, yeah, that would be great.
Yeah. Okay.
Okay,
that's it from me. Thank you. One more, just completely vague question, if you don't mind. It's just again.
Go for it.
Free associated, but if I could just, one way of getting something that looks sort of gravitational from a matrix integral is to move from eigenvalues to density of eigenvalues. And it's sort of gravitational because it's like a continuous function.
Right.
From that point of view, I was wondering, it's probably completely off of talking, that's probably a very stupid question. But if I were to sort of change, I took a one matrix model, just a matrix integral, like Gross-Witten-Wadia matrix integral, that kind of thing. And I changed variables from the eigenvalues to the density of eigenvalues.
Yeah.
I had vaguely thought that was an analog from moving to field theory to gravitation.
Yeah.
And now, in this way of thinking of it, I don't see any discreteness in the probe at leading order and large n. So the very vague question was, why should I have expected that if I was away from double scaling, I would get something discrete?
Yeah, morally, what's happening, I think, is that I think it's a great question. I don't understand. So there is, I think, actually, the intuition you said, my pedestrian understanding is that there is a precise version of that statement, which is that there's some map between a general matrix integral and the C=1 string, where the density of eigenvalues is related, whatever. There's this map to the fermion description, right? So that kind of, but so then the question becomes, how is that C equals 1 string description related to the dilaton gravity description? I think there should be a connection there, but it might actually be non-trivial. I kind of think it's non-trivial. But let me just say that I think where the discreteness is coming from, the dilaton gravity description, is related to the fact that there's a minimum and a maximum energy. And so you can only really probe times, up to fine enough, up to there's a limit to how sharply you can distinguish times morally.
Right. So the discreteness is coming from taking very seriously the statement that the matrix is a Hamilton. Right? Because that's
yes. I think that's right. Yeah. Right.
Okay.
Right, which was not how it was done back in the day, right? That's sort of a new input.
Right.
But I think that perspective maybe leads to a different worldsheet description or something. I'm not sure. There's some duality happening, I think, that we haven't understood, that it would be great to understand.
Thank you so much.
Yeah.
Okay, that's it from me. Okay. Thank you. That was a great talk. Thank you so much, and thank you for the patience.
Thanks for letting me talk. Sorry again about all the confusion about timing.
No problem at all, and thanks for the great talk.